Well, hello. Welcome to this video in which I'm going to show you a little calculus that we use when we're trying to calculate potentials of what we refer to as continuous charge distributions. These can be things like disks and lines and maybe cylinders or spheres, circles, things like that. And some are surprisingly easy, certainly easier than the electric field calculations we did like this. Electric fields had the complications of being vectors. So we had all these components to deal with. Um, we had inverse squares, which tended to make things a little more complex. Potential, you'll find, is actually a little easier, mostly because there's no vector stuff to deal with, but also just because the form that the equation takes, and I'll remind you of what that is. For a point charge, that's depending on how far you are from the point charge, we'll call that d, it's just kq over d. So what we have here is this dot. And the complication here is, well, you can't say that that charge is any particular distance from that dot, because some of the charge, like right down below it, is close, and some on the very ends is certainly far. And this, I hope you'll recognize, calls for something like calculus. So a few things that are similar to what we did in the electric field calculations is, I want you to imagine a little slice of this charge here. And we'll call this, because we're going along the x-axis, we'll call this tiny little width a dx. And then x is how far that little piece is from the origin here that was provided on this problem. This is actually a problem you might be seeing for homework. I'm not going to do the whole thing, but I'm going to get you a good start. So that's going to be helpful in describing some things. We're also going to have a distance we'll refer to as y. Y will be how far the dot is above the very center of the charged line. And we have a charge per length measurement that you'll recall from when we did electric fields. We describe as a charge density lambda, charge per length. So what we're going to do is we're going to put this all together and we're going to say, all right, let's find the value of just the potential due to that little chargelet there. I call that a chargelet, the little piece that's on that dx sliver of the line. And so we'll call this just a little piece of the potential that we're going to eventually calculate. So it's still kq over the distance, but let's describe this as k and then dq, a little piece of the charge. And then for our distance, I'm going to use, I'll have to draw this in a different color. I'll use green because it'll stand out. What distance is that? That's that distance right there that we'll just call generically r. I'll leave that in green for you. And then we're going to have to substitute in, because we can't perform calculus where we have what looks like q to be a variable, but then r certainly is going to be a variable, because if we pick a different little chargelet there, maybe further out, then r is going to be bigger. So this is the part where we try to put everything in terms of one variable that we can actually integrate over. So you may remember that because the charge per length is lambda, so is the ratio of the little chargelet to the tiny little length dx, which means I can replace dq with lambda dx. And then what else can we replace? Well, r certainly relates to what x is. Remember, x is how far our little chargelet is from the center of the line. And as we move further out, that gets bigger. So the relationship between r and x, and you see y there, is r is the square root of x squared plus y squared. That's just a little Pythagorean theorem length. So that actually now is in terms of everything that's a variable, x, and everything that's just a parameter, like k and lambda and y. So we're now ready to do the integration. So if we integrate both sides, we're going to get the sum of all the little contributions to the potential, which is going to be the actual potential. And then we're going to get the integral of, and I think what I'm going to do here is I'm going to get rid of this first because I like to take all my non-variable stuff, all my parameters, and just pull those out into the front. So I could take my k and my lambda out there. And then all I'm left with on top is dx. And then on the bottom, of course, I have the square root of x squared plus y squared. And then we want to talk about our limits. Now look at your variable. Always know what your variable is. In this case, it's x. And you just ask yourself, okay, self, how big can x get for all the little pieces of charge that I need to look at? Well, certainly it can get all the way out here to the right end of the charge line and then all the way to the left end. And how far is that? We use limits of L over 2 and negative L over 2. And then it becomes a calculus problem. I'm actually going to stop here and not perform the rest of this for you because I want you to get used to how you go from here. Because if you're either not in calculus or you forget this calculus, you might wonder what to do. And I'm going to suggest that your textbook probably has a nice little reference section at the end where they've got common antiderivatives like this. If not, you could certainly Google it. When I was in college, I actually had a little booklet that had common calculus solutions like this, and I just needed to look at it a lot. This is not a calculus class you're in, but you ought to be able to at least look up those and perform the integral once you know them. So I'm going to leave it at this, and hopefully you've seen enough there that if you have a different kind of shape, you can set yourself up a little integral and find the potential this way. So I'll leave it at that, and good luck from here.